Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Department of Mechanical Engineering. The name of the course is Mechanics of Solids. For the third semester Mechanical Engineering students, this course is a core subject. Today in this session, we are going to study the problems on modulus of elasticity. What is modulus of elasticity? Mathematically, it is defined as the ratio of stress to strain. Here sigma is the normal stress and strain is the normal strain. And modulus of elasticity is denoted by the letter capital E. The unit for modulus of elasticity is Newton per meter square. Modulus of elasticity is related to the normal load. When the normal load is applied, normal stress comes. The normal stress proportional to normal strain. When normal stress is proportional to the normal strain, the ratio of there is a constant of proportionality. That constant of proportionality is known as the modulus of elasticity. Modulus of elasticity equal to normal stress by normal strain. If the normal stress is tensile, then the strain is tensile strain. If the normal stress is compressive stress, then the strain comes the compressive strain. And there is another strain is known as the volumetric strain. The volumetric strain is denoted by epsilon V, that is delta V, change in volume by actual volume, original volume. It is the fraction. That's why the unit for volumetric strain, tensile strain and compressive strain are unitless, 0. So here a square steel rod is having a the section is a square cross section, that is 20 by 20, is to carrying an axial load. The axial load here, it is the compressive axial load. Then calculate the shortening in a length of 50 millimeters. Shortening means a decrement in length. Decrement, that is delta L, decrement. And the modulus of elasticity is given here. It is 2.14 times 10 power 8 kilonewton per square meter. So by using this formula, the formula of modulus of elasticity, that is sigma by epsilon, that is normal stress by normal strain. Here it is the compressive load, that's why it is compressive stress over compressive strain, epsilon C. The compressive stress comes from the formula for compressive stress is load per area of cross section. The load is here, it is 100 kilonewtons by area of cross section, 0.0004 square meter. From these two parameters, we can calculate compressive stress. And E was given here. The modulus of elasticity is known value. The unknown is epsilon C. That E equal to sigma C by epsilon C is delta L by L. L we know, that is the total length. The axial, we want shortening. Yes, for a length of 50 millimeters. That 50 millimeters is the length. From that, delta L is to be calculated. So thus we have calculated the delta L value, that is 0.0584 millimeter. The next model is related to a hollow cast iron cylinder, that is 4 millimeters long and 300 millimeters diameter, outer diameter, and the thickness of metal is 50 millimeters, is subjected to a central load subject to the central load on the top when standing straight. The stress produced is 75,000 kilonewton per square meter, and we are going to assumed the Young's modulus value is 1.5 times 10 power 8 kilonewton per square meter, and we have to find the magnitude of the load, what is the load is acted, and also longitudinal strain epsilon L, and total decrease in length. We want decrease in length. Strain, if we know the strain, then if longitudinal strain equal to delta L by L, from the delta L by L, delta L can be calculated. And it is the magnitude of the load. What is the load which is acted on that? The load which is acted to obtain the stress of. The stress is obtained 75,000 kilonewton per square meter. So stress equal to load per area. We have to calculate the load, but we know stress and area. What is that area of cross section? This is the hollow cylinder. What is the area of cross section for hollow cylinder? A equal to pi by 4 times capital D square minus small d square. We know the outer diameter and inner diameter, that is capital D, inner diameter minus 2t, that is inner diameter. That inner diameter is calculated as 0.2 meters. And outer diameter, the known outer diameter is 0.3 meters. Substitute over here, then we can know the area of cross section, area of the hollow cross section of the hollow cylinder or hollow pipe. Then substitute over here, that is sigma value known. The sigma value is 75,000 kilonewton per square meter, and area of cross section area we can calculate. Then multiplied P equal to stress times area, then the load can be observed. The observed load is 2945.2 kilonewtons. And one more important thing, this is the first objective. The second objective, we know the stress and we know E. Stress unknown. Then what is the epsilon L? Then sigma by E. From that, change in length, strain comes, longitudinal strain. After knowing the longitudinal strain is calculated as 0.0005. After knowing epsilon L, that is a delta L by L, we know that the L is 4 meters, epsilon, that is 0.0005, L is 4 meters, and delta L can be studied, that is epsilon L times L. The epsilon L is 0.0005 and delta L is 4 meters. Then it is 0.02002 meters, that is 2 millimeter. 2 millimeters is the decrease in length when the load is applied. The total load applied on this, here it is 2945.2 kilonewtons. That is total is 2.945 meganewtons Mn. This much load is applied. The deformation, the decrease in length is 2 millimeter. Why it is happening? Yeah, there are various factors. The factors affecting in order to get obtain or observe the low decrease in length, that is 2 millimeter delta L is. Because here various parameters affects this deformation, decrease in length, decrease in. That is the various parameters are, let us take this E equal to stress by strain. Then from that, strain equal to sigma by E. So delta L by L equal to sigma by E. Delta L equal to sigma L times E. Sigma is the pressure P, L by AE. This is the formula. Delta L equal to P by P L by AE. Either in the case of tensile load, it is the deformation, increment in length. In the case of compressive load, it is the decrement in length, reduced length. Now here, the delta L depends on load, the type of load which is acting on the cross section, and the length of the body, cross section of the body, and the type of material the type of material that is related to property of the material is modulus of elasticity. Delta L depends on various parameters. Type of load, if it is a tensile load, instead of decrement, there will be an increment in length. In the case of compressive load, it leads to delta L becomes the decrease in length. Delta L equal to PL by AE. And type of load, next, the length. If length is more, okay, it is proportional, delta E is proportional to the L. If length is, it depends upon the L and also area of cross section. If area of cross section is hollow or type of area of cross section are solid, if the value of area of cross section is low, then delta L becomes high. It is inversely proportional to effect. If E value is more E value, delta L becomes low value. With low E value, delta L becomes high value. So here delta L is dependent on P, L, A and E values. If we consider the stress value, the stress equal to sigma delta L E by L. So here the stress which is coming or occurring in the body of a material is dependent on modulus of elasticity and also strain. Delta L by L is nothing but strain. So when the stress is increasing, the strain also increases. Provided if E is the constant, we are making the constant, the property of the material it is constant. The variable here it is the strain. It is a constant, it doesn't change because the material property. If a stress is increasing, the strain will increase. The stress versus strain, drawing a diagram. The diagram is known as stress-strain diagram. Stress versus strain diagram. The slope of a stress strain, that means the ratio of the stress by strain, is known as the modulus of elasticity. So for again coming to another picture, if you want to find out the study the stress and strain properties, so we have to study the mechanical properties. There are two here stress strain diagrams. The stress strain diagrams for brittle material is different from the stress strain diagram for ductile materials. This brittle and ductility comes under the category of the properties of materials. Coming to next, what are the properties of the materials? Mechanical properties of materials. Mechanical properties of materials. There are various mechanical properties of materials. First one is ductility. Second one is brittleness. Third one is elasticity. Fourth one is malleability. So another one is hardness. But stress strain diagrams we are going to study for ductile materials and brittle materials. What is ductility? When the load is applied on a material, the material will be deformed. The material is deformed under the tensile load. Brittleness also deformed, but there is very short deformation and fracture takes place immediately. Ductility is the property, the application of the ductility material property is highly useful in making jewelry ornaments, where suppose if it is a golden ornament, the gold is having a property of ductility, so it will be deformed in a thin wire, from thick wire to thin wire or low diameter, because of this ductile nature. And when you apply the load for ductile materials, we'll study in detail in coming sessions. If you draw a stress and strain diagram for ductile materials, the stress strain diagram becomes in the shape of a so there is a limit in this curve. This is the stress versus strain curve. Stress strain curve is highly important in order to study the strength of materials. This is the point, the fracture, and it is the point ultimate sigma ut, ultimate strength point. If you measure horizontally, this is the level. Now there is a point is there that is called elastic limit, elastic stress sigma e point. Within this zone, that zone is known as elastic zone. That within the elastic zone of the limit, within the elastic limit, that limit is known as the limited stress of elastic. Beyond that, it becomes into plastic zone. That zone is known as, that stress is known as elastic stress. Where what will happen? The stress is directly proportional to strain. This after removal of the load. When the load is removed on a material, it regains its original shape. Suppose if you take a rubber band, if you apply the load, there is deformation. Remove the load, it goes again to its original shape. That means that rubber is having a property of elasticity. So under the cyclic, if the load is applied within that limit, if you remove the load, when the load is applied, there will be a strain. If you remove the load, the strain goes back, it becomes zero strain. This cyclic load within that limit is known as elastic limit. Now here, for ductility, this gold is having a property of ductile nature, that's why it is deformed for a limited length. Whereas brittle nature, for a brittle nature, brittle means there is no, if you apply the load, immediately breakage takes place. So we will study in brief in coming sessions the stress strain diagrams of ductile and brittle materials. But here we are focusing only on mechanical properties of materials. So when you apply the tensile load, the deformation is very small in comparison to the material which is having ductility. Brittleness, immediately fracture takes place. Examples for brittle materials are glass, one of the glass material and some of the plastics brittle nature. And you can see the biscuits are made of a brittle crackjack. If you apply just like it breaks immediately. Not when it is spoiled a biscuit, it may be elongated. But the point is that the glass and ceramics are brittle nature. Okay, but what are the advantages of brittle nature? It is having brittle materials are having more damping absorption. The damping is high. But here the brittle materials has disadvantage of brittle materials in it when you apply the tensile load. So it breaks materials immediately, fracture, it reaches the fracture limit without any intermediate limits, no elastic limit, no plastic, no ultimate direct. That is only fracture is equal to ultimate only. That is what. And as we have studied already discussed about elasticity. Now here this ductility and brittleness we have studied under tensile load. What is malleability? If the material is applied under compressive loads, it is deformation. The thick sheet is applied compressive load, it will become thin sheet. Okay, that is called property of the materials, that known as the malleability. So what is a hardness? The hardness is the property of the material which can't be scratched, which can't be deformed, okay, which is having the resistance to deformation, indentation, scratch. Under those things, the material remains stable. Then it is known as hardness. The hardness is defined or measured experimentally with the help of a hardness tester. Hardness tester. In that, there are different scales, different Brinell hardness, Rockwell hardness. And one more important property is toughness. This toughness is measured experimentally with the help of impact testing machine. Impact testing machine. Again, there are two types of impact tests are there. Number one, I-joint testing. Another one is choppy testing. So this toughness is the property of the material, and also one of the property of the material is creep. Another one is fatigue. These are all various properties of materials. The fatigue is under cyclic loads. It is able to withstand fatigue strength. When the body is subjected to cyclic loads, it should withstand for that load under loads. Then that strength of that material is known as the fatigue strength. The cyclic loads example is that when in the case of spindle, in the case of CNC machine, it is subjected to certain load, it continuous rotates. The spindle is subjected to cyclic loads. And here, how to find out this fatigue strength? So we have to find out, we have to make the under standard, we have to prepare the samples and we have to test them. At what cycle of loads it is having infinite period of time, because within the zone it is having infinite cyclic loads, it doesn't affect. Then that strength of that limit, that strength is known as fatigue strength. The creep is the function of the time. When it is loaded carrying with a period of time, there is a deformation. If it doesn't deform for a period of time, it is having a creep strength. Now these are all our properties of materials, material properties. The material properties are again ductility, brittleness, elasticity, malleability, hardness, toughness, creep, fatigue. Okay. Now here, this hardness can be studied experimentally by using hardness test tricks. What about ductility and brittleness and elasticity? These are all studied by using UTM, Universal Testing Machines. In the universal testing machines, the load is applied, the specimen is fixed at one end, and the load, tensile load, is applied on the specimen, gradually increasing the application of the load. Then we can observe the strain in proportional to the stress. The stress strain diagram can be drawn by using a UTM, Universal Testing Machine. And ductility, brittleness and elasticity can be studied in this UTM, Universal Testing Machine. Okay, these are the various properties of materials. And the examples, what is the usage of this malleability property? Suppose galvanized iron sheets are there. The GA sheets are manufactured in malleability by applying malleable or compressive loads, then it becomes thin sheets. To prepare a thin sheets or thick sheets, to prepare the thin cylinders, shells manufacturing, we need this property of the material, this malleability we should have. The brittleness is having, for that means immediately cracks propagation. Cracks occurring takes place if the material is having the brittleness when you apply the compressive load. So for every material or any component, if you are manufacturing, based on the application of that component, we will consider this one of the properties. From this list of the properties, we'll consider it based on the application. For making the gold and silver is having ductile nature, that's why that gold and silver materials are used for ornaments, different vessels, different preparations based on this application. And one more thing, the elasticity, malleability is applicable for fabricating the shells, boilers, etc. And toughness and creep and fatigue, wherever cyclic loads are there applying, especially under rotating components. There is a chuck is mounted on a shaft. Okay, that means when chuck is rotating, CHUCK chuck, it is a component of a lathe machine. When chuck is under rotation, that means the shaft is subjected to cyclic load. So that means the shaft should have a fatigue strength. If the shaft is having a ductility nature, when there is a load applying, it will bend. Bending stresses leads to deformation, and its bending takes place. So based on the utility and the requirement, we choose the material. Those are known as selection of materials. And we consider these properties which are mentioned here, and go for fabrication such a way that we can fabricate or manufacture the robust design component. So if the person is, suppose, chair we are sitting, that chair should have withstand what type of load, the compressive loads. It should withstand compressive loads, and whatever material and whatever type of material. And finally, we have to consider the cost of the materials. So the chair, the more strength is that a diamond. Yes, a diamond, you can prepare the chair. What are the affordable people? So the thing is that it's optimum design, optimum things, how much load the chair should withstand. In proportional to that, we'll select the material by considering the cost of the product, final cost of the product. So in that manner, we'll fabricate the components by using and by considering these properties. These are all mechanical properties, and another properties are called thermal properties also. If the component are, if the body or components are exposed to at various temperatures, then we have to consider thermal properties of materials. But here the mechanics of solid subjects, that's why here we are considering the mechanical properties of materials. Okay, so in this session we studied what are the mechanical properties of the materials and solved few problems by using the formula, that is modulus of elasticity is related to stress by strain and how to what type of strains. And here also we consider the strain is the fraction of deformation, that is normal strain, and the modulus of elasticity is related to the normal stress and normal strain. And the stress strain curve we have studied not in detail but just a glimpse of stress strain curves. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.